Hello, everybody. My name is Louie Mattucci. I'm a systems engineer with Arista. I'm out of Columbus, Ohio, and thank you for the honor to speak with you today. As you can see on the screen here, my talk is going to be about networking for AI. So probably most of you are on the data or the software side. I'm on the infrastructure side. So hopefully this will be easily digestible as you're also enjoying your lunches. And we'll just dig in here and get through this pretty quickly. So in the networking space, we build leaf spine networks, right? So your computers, your servers, they attach to what we call the leafs, and then those leafs attach to spines, and to get between leafs, you bounce off the spine, you come back down, you hit another leaf, and that's how servers talk to each other. Today, most of those connections on the server side are done at like 10 or 25 gigabits per second. And sometimes on the storage side, if you're connecting your storage to an Ethernet network, that can be done at 25, 50, or 100 gig. And then typically those uplinks between the leaves and spines, they tend to run more in the ballpark of 100 gigabits, right? So what happens when your director of R&D comes in and tells you, hey, I've got this new GPU system. It's full of NVIDIA H100s. I've got 8 GPUs in this thing, and it's got 400 gig connections. So what you see on the screen here is basically what one of these massive DGX systems from NVIDIA might look like. You can see you've got a couple of CPUs, and you've got a total of 8 GPUs in this system. They're all interconnected by these PCIe switches. There's a one-to-one relationship between these GPUs and their upstream network interface cards, or NICs. And so what's interesting is within the system, those GPUs talk to each other. The communication doesn't leave the box. There's usually some GPU native fabric. So in the NVIDIA world, that's called NVLink. In the AMD world, that's their Infinity Fabric. So within the system, there's a native communication plane between those GPUs. But when you need to talk GPU to GPU outside of the system, that's where you have those northbound interface ports. And so, going back to the traditional network, you're talking about 10, 25 gig. In the new world, we're building these back-end networks where we're attaching these GPUs at 400 and soon to be 800 gigabits, okay? So the front-end network is, what we've always been building, these traditional leaf spines, 2,500 gig. These new networks to interconnect these massive GPU systems, these back-end networks, typically they have 400 gig connectivity to the GPUs, and they're not oversubscribed at all. And so what that means is for every 400 gig connection you have down to a GPU, you have a matching 400 gig uplink to the spine, okay? And so, we're typically used to like a 2-to-1, a 3-to-1, maybe a 4-to-1 oversubscription ratio in the front-end network. These back-end networks have to be fully provisioned with no oversubscription. So this part down here is what's new to most network engineers. And ultimately, we're scaling these networks out to 16,000, 32,000. I think the largest one that's in existence today, the XAI cluster down in Memphis, Tennessee, I believe is 100,000 GPU cluster. And so, as we build these networks larger and larger and larger, there are some optimizations and some tweaks that we have to put in to make everything work properly. But what do these applications actually care about? There's two main metrics that we talk about in the networking space, JCT and TCN. JCT is job completion time. This is from the time, like let's say a training job is launched until that job is completed. TSN specifically is a subset of that JCT, where it's basically how much time did that job spend just traversing the network, okay? And so we measure some of these things down in the millisecond ranges. And so very small efficiencies on the network transport side have big valuable meaning to the GPU guys. As you know, sometimes they're training these jobs, they might take days or weeks or months, okay? So the more we minimize that time spent in network, ultimately the better off and the higher utilized those GPUs are. And so there are some problems, you know, with, in the networking space, we do things like, we have incast, like shown here on the far right, where you've got data coming in from multiple sources, all trying to egress the same physical port. We have flow collisions, transient oversubscription, but basically what we're doing in the Ethernet side is we are tweaking and tuning those connections to minimize the time spent in networking and, you know, some of those other problems like collisions and the like. So what we're showing here on this slide is just, you know, if that pink block represents vanilla Ethernet, the blue portion there represents the optimizations that we get on the Arista side when we do some of our magic within the Ethernet protocol. And so we bring a full portfolio for training of these clusters. We have, you know, you can see these 16 slot chassis where we can get like over 500 ports of 800 gig within one form factor managed as one device. And so that's typically large enough for most companies that are experimenting with these GPUs on premises, right? We also service a large portion of Microsoft Azure's global backbone as well as Facebook and Meta. So some of our customers are building these systems on premises, others are renting from the cloud providers, and we provide a lot of the transport even in those cloud situations. And we have some optimizations here, which just for the sake of time, I won't go into too much more detail here. But the real takeaway is that, you know, we optimize for power, we optimize for latency, we optimize for packet loss, and, you know, we maximize for observability as well. And so one of the key things here is the quality of the operating system that's running on that hardware. Arista's operating system is known as EOS, or the Extensible Operating System. And so there are standards bodies out there like NIST and MITRE who publish and catalog CVEs, common vulnerabilities and exposures. And so the higher your CVEs, the more you have to patch your systems, the more downtime you potentially have, the more fragile it typically is. And so, you know, you can kind of see some of the numbers there. And the other important thing is on the optics side, so the transceivers to interconnect between our switches, which would be shown on the left here, and then the NICs or the GPU systems, which are shown on the right. So how do we achieve 400 gig? How do we achieve 800 gig connections between our switches and those systems? We have a lot of detail here, and we've got a full portfolio of that equipment as well. The next thing that I just want to mention is the UEC, the Ultra Ethernet Consortium. This is a group of companies that have come together to build more enhancements into Ethernet to benefit AI. And so you can see who some of the representatives there are. The main problem that they're working on is a transport protocol to replace RDMA over Converged Ethernet, also known as RoCE. And there's load balancing challenges to figure out. There's scale challenges to figure out. But ultimately, I'll leave you with this, if there are any hockey fans out there. So Wayne Gretzky talks about, the reason he was so successful is that he would skate to where the puck was going, not to where it's been. So, I'm a firm believer that IP and Ethernet always wins. So we used to build separate networks for things like telephony and video conferencing and broadcast video and storage and high-performance compute and AI clusters. I believe that, with the optimizations that we've been talking about, that all of those things are ultimately converging to IP and Ethernet. And so I've got 8 seconds left. If anyone wants to keep in touch with me, you can visit our booth. We're Arista Networks, and there is a QR code with my LinkedIn profile. So that's all I got. Thanks, everyone.